Linked list, let's do it. Folder. What's up, Salim? For me, it's morning. For some people, it's night. Oh, I don't have my phone. I had some issues today. Oh, it's 312 in Hotch. Ugh, it's just the way it rolls. Like my last semester, I had everything in NSC 215. I got Hotch and Cook next semester are my two classes. So I'll be coming from Cook over to Hotch, so I won't even be there when a lot of y'all get there. Morning, Darmy. Upcoming alarm. Should I do, how much time we got? Should I do the countdown? I think the countdown might be helpful for countdown timer. Might be helpful for people watching the VOD. 5. Here to learn Java for fun. All right. It will be fun. Linked list, stacks, and queues today. It's going to be a blast. All kinds of good stuff. Oops. Lecture starts in... Probably should set up something fancier for this, but whatever. This works, and I don't want to mess with it. I don't want to build anything. I build enough stuff. And I can't navigate away from this. No. 116 and go? No. Not gonna happen. 312 and go, maybe someday. 116, nope. We just had the whole adventure of 116 in Scala, using some modestly obscure language. Not that Go or Scala are that obscure, but no, not 116. Just no. I wouldn't be too mad about 220 in Go. But I also hate Go. That's why 312 is not in Go yet. Go's a good language. I should probably explain that a little bit. Go's a good language, but it's very opinionated. It wants you to do things the Go way. There's one way that the developers of Go want you to code, and you have to code that way because it's actually compiler checks. I'd say the one that bugs me the most is that if a variable name starts with a capital letter, then it's public, and if it starts with a lowercase letter, it's private, which is just completely made up. Like the designer said, I don't know, this sounds like a good idea. Let's force everybody to do it that way. And seeing variable names that start with a capital letter just bother me because we don't do that in any other language. But we're actually forced to. The compiler forces us to and Go. And there's just a lot of little things like that throughout the design of the language where whoever made those decisions said, I don't know, I don't know. It just rubs me the wrong way. But Go might be better than C. So I think Go's getting a lot of traction because people would rather use that than C. Go or JavaScript, which is worse? Oh, I don't know. They're both good and bad for a very, very different reasons. Giving a definitive answer on that, for me personally, and people are gonna hate this answer, JavaScript bugs me less than Go bugs me. I've also written a lot more JavaScript than Go, so that also factors into things. If I, used Go a lot and just got familiar with it, I'm sure my opinions might change. I think changing to Go might be a little easier. Like, I have complaints with Go, but they're not real, like, they're not legitimate complaints. Like, the one I gave was a styling preference. Like, it's not that big of a deal in the long run. So I think exposing third semester students to Go might be easier than exposing them to C, because they're not going to have the same arguments I have. A third semester student's not going to be like, holy crap. Well, some of them might, but aren't going to be like, holy crap, variable names that start with capital letters? Wow, this pisses me off. But for me, who's been coding for way too long, 20 years? When did I start? 2008, I guess, is when I formally started. It's not quite 20 years, 14 years. I've been doing this long enough that I'm set in my ways with some things, so it's a bigger deal for me. I'm just an old grumpy guy. But in 220, you wouldn't have that same issue. All right, so let's get started. So I should probably start with an overview of where we're at. So we're going to do linked lists today. Right now, you have everything you need for programming test 2. Programming test 1, we had the expected deadline this morning. I looked at the stats. I think, actually, let me get a legit number. The actual number for you. How many of you met the expected deadline? Is 70. All right, hey, that ain't bad. Actually, I think a few of you just got credit after I pulled the results. So maybe like 68, 69-ish. I'll look at that when I'm offline. And then out of a total of, so 70 have credit right now out of a total of 76 who have made a submission, at least one submission. So 6 who have made a submission made at least some attempt. Maybe it was just a panic, desperate submission in the morning. I don't know. I didn't look into them. But made some submission and didn't get credit. It's those of you who did not make any submission, if I can do quick math, 18 of you who did not make a submission, you're the ones I'm really concerned about. If you waited till, like, we're 2 weeks into a 6-week semester right now. We're a third of the way through this thing. At least we will be in 2.5 hours. We're a third of the way through this thing. So if you still haven't even started programming task 1, you're probably going to fail. Like, there's no sugarcoating it with this semester. With this lecture, we're about to get really into the thick of things. The first real pickup in pace of the semester, in that you'll have programming test 2 that you're working on, that you're hopefully already started. Programming test 3, which you should be starting today. And 2 quizzes that you have to study for that we have to do on Tuesday. with all of that coming up, if you're still working on programming task 1, honestly, you're probably not watching this lecture either. At least not today. You're probably not watching it. You're just going to fail the class. There's no sugarcoating that one. There's no coming back from that. You can't do this. I think it's difficult to do this course in a 6-week semester. If you're turning that into a 4-week semester, you're just going to fail. And there's nothing I can do at that point to save you. You'll come to office hours in 2 or 3 weeks and say, Professor, how do I pass this class? And there's just nothing I can do for you. Sorry. But I wish I could, but there's just nothing if you're not going to start. But most of you did start and you got credit. So for those of you who are on track, we have the quizzes coming up. The logistics for the quiz, I'll send out an email. I probably should send that out today just to make sure everybody's on the same page. Because, the students I just mentioned who aren't keeping up with lectures in the class, I still want them to have the information so they're not blindsided by this. But I'm not going to go live at 11 a.m. on Tuesday. So when we have the quiz at 11 a.m. on Tuesday, I'm not going to be on YouTube. There won't be a live thing. I was thinking about going live just for people who don't know, didn't pay attention, just to say, hey, there's a quiz. Make sure you check your email or something. But what I'm going to do is email out the quizzes at 11 a.m. Eastern time. So right at what would be the start of lecture, I'm going to send out an email to the entire class and say, here's the quiz. It's going to be an electronic version of the quiz. It'll have the 2 sections, the 2 programs that you have to trace. You're going to create your 2 memory diagrams in any way you prefer and then submit it electronically to Autolab. We'll have an assignment. We'll have a quiz assignment where you'll submit your images, submit your electronic copies of your memory diagrams. I'm leaving it up to you all how you want to handle that logistically, how you want to create an electronic version of your quizzes. But my recommendation, what I would expect, I think it would be the easiest way, is to take a sheet of paper and a pen or a pencil if you want to erase your mistakes, and write out your memory diagrams. Say memory diagram 1, and then draw out your memory diagram 2, draw out your memory diagram, and then take a picture with your phone. Take your phone out, snap a picture, and then on your phone submit to Autolab, upload those images. I'll have 2 different submissions, one for classes 1 and one for data structures 1, just to keep things more organized on the back end, so we can get those graded and get the grades out in a more consistent, more uniform manner. And yeah, what else do I gotta say? I'll give some slack. So the quiz itself is 11 a.m. to noon. I should have that on right here. I probably should say specifically it ends at noon. It will be 1 hour, so you have 1 hour to do the quizzes, but I'll allow some leeway in the submissions, especially for this first one. I probably will for all of them, but I'll add some time to that so you have time to do the scan. If you stop working at noon, I want you to still have that full hour to work on your memory diagrams. And then I'll give some time for the first one, probably 15 minutes before I close submissions, so you can get your electronic copies, get it scanned, whatever logistics you have to work out. And I recommend practicing that beforehand, by the way. It should go without saying, but so many students don't practice things. They don't prepare. I see that, not to get too off track already, but with student presentations, they get to the front of the room and they panic, like, I don't know what to do. Like, plug in your laptop and pull up your presentation, bro. And they just get so lost. Like, come to the room before, like the night before. But anyway, I would practice that. Snap a picture if you've never uploaded a file from your phone before, for example. It can be weird to find the files. The first time I did it, I'm like, where is that image? Where is that stored? To go into the file picker in Autolab. All right, but that's coming up. So I'll send an email at 11 a.m. on June 13th, on Tuesday, June 13th. You'll get an email from me, and it's going to have the code for the 2 quizzes, and then submit those memory diagrams for those pieces of code electronically on Autolab. So if there are any questions about that, I'll be happy to take them throughout the lecture whenever you have a question about them. And I'll send out an email explaining that again. I want to make sure nobody misses that. I don't want anybody coming to me and saying, well, I didn't know what to do for the quiz. I showed up on YouTube and there was no live. There's not going to be a live. And I'm not going to do a Zoom meeting either. I thought about it, but I don't think there's any advantage to that. It would be cool to see. 220 in Go would be probably, if any course is going to be in Go, probably 220 would be the coolest one. Or C and Go, and then do comparisons between the two languages. I think that would be neat too. That one would be an unpopular decision, but I'd like to see that. It would be the most educational value for your dollar to see both languages in comparisons. Then you do each homework assignment in both languages. You get tons of practice. You would know a lot of stuff by the end of that. But then the complaints would come in and we'd have to change it back. This is too hard. Why are we doing two languages? But anyway, let's get into it. So we want to talk about linked lists today. So let's talk about what a linked list is before we... 8 minutes of intro. I gotta cut down my intro speeches. So linked lists. Before we talk about linked lists, I want to talk about array lists and arrays first, and talk about how an array is structured. Talked about this very briefly, and this will be pretty brief here as well. But I want to bring up arrays for comparison because this is the data structure that you've used so far. You've used lists in Python, you've used arrays in JavaScript, and I keep meaning to look this up, but I'm pretty sure lists in Python are effectively arrays, that they behave like arrays. I don't think they're actually built on linked lists. They just call them lists. I'm pretty sure, but... I've never been 100% on that, and I keep forgetting to look it up. But when we're programming, they do behave like arrays. Or rather, like array lists, which is a fancy array. We usually don't deal with arrays directly. You will in 220. Speaking of 220, you'll deal with arrays directly. We'll see it very briefly later this semester, but I'll show you a trick to just turn an array into an array list and then not worry about plain arrays at all. But arrays, what they actually are, is one continuous block of memory. When you ask the operating system and the JVM for memory for an array or an array list, I'll say arrays while I'm explaining this because all this is going to apply to vanilla arrays, and then I'll talk about the difference, how array lists handle that. But an array is one sequential continuous block of memory. So you go to your operating system, you go to your JVM, and you say, give me a chunk of memory. I need a chunk of memory that can fit 20 values of the type that I'm going to store. You get that chunk of memory, and what the operating system will return is the memory address of the first location in that chunk of memory that it allocated for you. And then you can use that first memory address to access any element in the array by doing just a little bit of math. So we have the memory address for the first element in the array. That's what we have. That's the reference that's stored in our variable, which is just a number. A memory address is just a number. It's the hex value of it's the number of that memory address in hex. We represent it in hex because it's binary, but it's just a number. So we have a number, and if we want to get any value at any particular index, we're going to take that index value, multiply it by the size of an element, specifically the number of memory addresses or the number of bytes that it takes to represent one value in your memory, in your array. Multiply that index by the size of an element, add it to your first address, and you have the memory address of the value at that index. So if the index is 0, this zeroes out, and then you just get the first address, which is the very first element. So index 0 is the first element, which is why we start with 0. If you ever wonder why do we start counting at 0, this math really works out if you start at 0, the first element at 0. If this is 1, you're going to go to the first address and then advance the size of a single element, and that's going to be your second element in your list. If this is 2, you go 2 elements down and you find the memory address for what you're looking for. So with one multiplication, one addition, you find the exact location in memory of the exact value that we're looking for. This is something called random access memory. It's on my next slide a little bit more. Random access. I guess I don't put it together in this slide. But this is called random access. But there's a big implication here. An array cannot cannot change size. You can't grow an array, and you can't shrink an array. You can pretend that an array shrinks, but it doesn't really shrink. You asked for a certain amount of memory. You said, I need enough memory to store 10 doubles. And that's the amount of memory that you got, and you got the memory address of the first memory address of that block of memory. But that's it. You might not use up all that memory. You might not fill up the array, but the array is size 10 in that example. So if you want to add an 11th element to that array, guess what you can do about it? Nothing. You can't add an 11th element to that array. It won't work. It doesn't work like that. Because you need a memory address that's not allocated to you. You need some space that's not allocated to you, and you need very specific space. You got this chunk of space, are my hands on screen? You got this chunk of space for 10 elements, and you would need this next chunk of space. Very specific memory addresses to store the next bit of information, that next element. But that's not how operating systems work. You can't go to an operating system and say, can you give me memory address 234? Doesn't work like that. The operating system's just going to go, screw off, man. That's not how I roll. You can ask an operating system for a specific amount of memory, but it's up to the operating system to manage where that memory will be. So you can't say, give me this very specific chunk of memory that I need for my 11th element in my array. Just doesn't work like that. Sorry, you're SOL. You can't do it. Cannot change size of an array because it's a continuous block of memory. It's one chunk of memory. It's one chunk of your RAM. And you can't just say, give me this location. Doesn't work. Can't do it. So array lists and arrays are stored in the heap. We only get a reference to the first element in the array list, and then we do math to find any other elements. And we do just that little bit of math, which I explained on the previous slide. So for example, if we have 32-bit ints, we're going to have 4 bytes for each value. Each memory address is to a specific byte. So if my first element is at index 200, memory address 200, my second one is going to be at 204 because my 32-bit int takes up 4 my mind froze. 4 bytes of information, 4 bytes of data. So 204 is going to be where my second element is, 208, 212, just a little bit of math, and then we're going to find any value in our array very quickly too. When I say just a little bit of math, I mean very fast. One multiplication, one addition is what we call O of 1 time. We haven't talked about runtime too much yet, or well, at all in 116. I think they mentioned a little bit in 115. But this is an O of 1 operation, constant time. It's one multiplication, one addition, no matter what index is, no matter how big your array is. It doesn't change the amount of work you have to do to find the memory address of whatever you're looking for. This is something called random access. And your RAM stick, your RAM, your memory in your machine is effectively one giant array. So everything is technically in an array. You can represent anything with an array because that is what we do. Everything's in an array, including linked lists that we're going to talk about. They're in an array because memory is an array. It's an array of bytes indexed by memory addresses. That's all memory is. And we call it RAM because it's random access memory. If you have a memory address, you can go right to that memory address and get the byte, the value that is stored in that memory address. So random access memory, this idea that we can go to any value with a little bit of work and find the element at that index. Random access. Very convenient, very fast, very efficient. All right. If there are any questions on arrays, I have the normal latency again, so if there are questions on arrays, I'll take them as they come in, but I'm going to start talking about linked list. So in comparison, linked lists are still sequential data structures. What this means is that the order does matter. I don't think I mentioned that when I was talking about arrays. Oh, and I promised I would talk about array lists. So array lists actually do work with arrays. We saw the code last time where an array list actually has an array as an instance variable. inside of objects of type array list. It actually works on top of arrays. So everything is stored in an array when you use an array list. Just you get extra features. And the big feature that we have is that array list gives you the illusion that your array can change size, but it doesn't actually change size. And a lot of languages do this. A lot of languages give us this functionality of, if you ever used a vector in C++, it works almost exactly the same way. It has an underlying array, and it gives you the illusion that the array can change size. And how it does that is it asks for an amount of space that's more than what you need. So it gives you a bigger array than what you need and just doesn't use the whole thing. So that's why we saw size as a separate instance variable in our array list, because size is almost always not going to match the actual size of that array, but keeping that size variable separate tells us how many values are actually being used up in that array that's bigger than we need. And then when we do run out of space in that array, we're going to create a new array. Array list creates a new array that's double the size, copies all of the values from the original array over to the new array, and then throws the original array away. We just throw it out. It gets garbage collected. It disappears. And then when we run out of room in the new array, we'll create another one, double the size again, and keep doubling the size until we can fit all the elements that the user's asking for. So it gives us the illusion that an array is changing size, but it's not actually. It's just doing some extra work under the hood. All right. So linked lists, what we came to talk about today, is sequential still. The order matters. Unlike, by the way, when I see the reason I'm saying sequential, as opposed to a key value store, like our hash maps are not sequential. You add a whole bunch of key value pairs, and some of you found this out. I said it in lecture, but you really get to see it in action in your best key method. How it, depending on like what you're debugging, and if your code just works the first time, you probably wouldn't see this. But if you're debugging, you'll notice that it doesn't iterate over your key value pairs in the order in which you inserted them. You'll sometimes get a strange order because it's a non-sequential data structure. Array list and linked list, these are sequential data structures, meaning the order matters. How you insert the elements, the order in which you insert them, will be preserved, and that will matter. The data structure will remember that ordering. The big difference is these are spread across memory. So instead of one continuous block of memory like an array was, linked list is going to be all over the place. And we're going to talk all lecture about what that means and the implications of it. So each time we have an element in a linked list, which we're going in a few slides, we're going to start calling a node. But when we have an element in a linked list, it's going to know what that value is for that element and also where to find the next element. And these elements can be anywhere in memory. Every time we need a new element for a linked list, we go to the operating system, we say, hey, I need space for a new element. And then we get that reference and then tell the previous element, hey, this is where you can find your next element. Here's the memory address where you can find that. And this way we can change size. Every time we need to change the size of the linked list, we ask our operating system for more memory. Say, hey, I got to add another thing to this linked list. Can I get some more memory? And it says, cool. Because we're not asking for a specific place in memory. We're just asking for anywhere in memory. And then we take that reference and link the values of the list together using those references, which is why we need to talk about references last lecture before we could ever dream of talking about linked lists in this lecture. By the way, if the references are still a little fuzzy, you got some catching up to do, you got some studying to do, because there's no chance of understanding linked lists if you don't know what references are. I shouldn't say it like that. This will also, if you're still fuzzy on how references work, this will be good review to help you catch up to understand references. But you do have catching up to do, hopefully that you can do during this lecture, because we will have examples that use references, of course, because linked lists have to use references. So we have separate objects on the heap with references to other objects on the heap. So what we actually store when we store a linked list is just a reference to the first element of the linked list, just like how an array was just the memory address of the first element in the array, and we use that to find the rest of the elements. A linked list is actually a reference just to the first element in that linked list, but that first element knows where to find the next element, and that element knows where to find the third element, and that element knows where to find the next one, etc., etc., etc. until we find a link where we say, hey, link, what is the next element in the list? Where can I find the next element? And that list says null. That means we found the end of the list. Once the link says the next link is null, that means there is no next link. We've reached the end of the list, which is something we call null terminated. Something that you'll get familiar with linked lists this semester, and you'll get really familiar with in 220 because everything's going to be null terminated, including your strings, which I'll leave 220 to explain all of that stuff. But here's your first exposure to null termination. Once you reach null, that means it's the end of the data structure. So we will see a lot of nulls in our code, and we're going to do a lot of null checks when we have linked list nodes. And it's one of the most common issues that students have when they have questions in office hours and Piazza related to linked lists. A lot of times they're not checking their nulls properly. Either they don't have a test case that checks for a null linked list, if that's the case, if that's the specific test case that's being asked for, or their code itself is getting a null pointer exception, which means you tried, I guess I'll explain it right now since I started. Null is the lack of a reference. And to take a reference and follow it to the object to which it refers, we use the dot operator. If you use the dot operator on a reference of null, well, null has no way of going to the heap to an object to which it refers because it doesn't refer to an object. Null is the lack of a reference. Null says there should be a reference here, but I got nothing for you. So if you ask null, hey, take me to the object to which you refer, you get an error called a null pointer exception and your program crashes. So if you see a null pointer exception, you missed a null check somewhere. You should have checked, is this null? If it's null, I'm not going to ask it for its object. If it is not null, then I can safely use the dot operator and go to the object. So here's our linked list class. This is the first version of the linked list class that we're going to see, and it has two values. As explained on the previously, this is what it'll look like in code. Node is the new word that we're going to start using, which contains the element, the actual value of this element of the linked list. So that value, which here is going to be hard-coded as an int, the value at this location of the linked list, and also a reference to another node, which is going to be the next node in the linked list. So a linked list is a connection, a sequence of these nodes where each node has a reference to the next node, and each node knows its value at that portion of the list. So if you navigate a list, you go to the first one, say, what's your value, and where's the next one? You say, get the value, go to the next one, get the value, go to the next one, etc. until you reach null. Then you can have all the values, you can iterate over all the values in the linked list. And we have a vanilla, plain constructor. When I say, I use the word vanilla a lot. I should probably stop doing that if that's confusing. But when I say vanilla, I just mean nothing special. We're not doing anything special here. It's just plain. Just a plain constructor. It takes two parameters, and it sets those parameters equal to instance variables of the same names. So we're using the constructor to initialize the instance variables, and we're not initializing the instance variables to any default values. We have to get those values from the constructor call. And we're creating a new linked list. I think I'm getting ahead of my slides here. No, I'm not. When we create a new linked list, we're going to create linked list nodes. So I have a linked list node that I'm creating with the value 1 and next of null. So first, after this first line, is going to be a linked list of size 1 with the value 1. Next is null, so there's no other nodes. And then I'm going to reassign first to a new linked list node with the value 2, and next being first, which first was a reference to this node. This new node is going to refer to first as next, and then the next, then we're going to replace first again with a new node with value 3, and next being first, which is a reference to this node 2. So I should have first being a reference to a node with the value 3, which has a reference to the node with value 2, which has a reference to the node with value 1, which has a reference of null. So I have the list 3, 2, 1 building this this code. If that didn't make sense, don't worry. We got a whole memory diagram going through this code later in today's lecture. Because that's a lot, especially seeing first 2 times in the same line. That tends to trip students up, so I'll explain that when we get to the memory diagram. I'll explain it a little better, a little more detail, more visuals. So each node, after running that code on the previous slide, first we'll refer to this node with value 3. Its next is a reference to the node with value 2. Its next is a reference to the node with value 1. And that node's next is a reference of null. So each node knows its value and where to find the next node in the list. And that really is a linked list. That's everything. I think that's not everything. Obviously, we have a lot more to this lecture to talk about. But that's the structure of a linked list. That's how linked lists work. That's what they are. That's how they're built. And the rest of the lecture is implications of this. How do we work with this? What does it mean? What do we do with these linked lists? Which is going to be, we're going to see some algorithms that we use. Size, find, toString, min value, just working with this data structure. And then we're going to build a stack and a queue using this data structure. And we'll talk about what stacks and queues are. First, let's do a memory diagram to solidify what we already have seen. We have this code that we just saw a few slides ago. As usual, I'm going to change. I think we've only seen this once so far, so I shouldn't say as usual, but you'll see this throughout the semester. I'm going to modify my code a little bit for the memory diagram just to save space. So instead of saying linked list node int, I'm going to cut that down to LL node. It was this line in particular. This line when it was linked list node int, linked list node int. This one went like way over here and it interfered with my memory diagram. So just a little bit of shorthand just to compact the slide a little bit. I'll do that throughout the semester. I'll usually mention it. Sometimes I'll forget probably, but I'll usually mention it. All right, so let's see the first line of this. First line, this is pretty familiar. Even then, I say that, but it was just 2 days ago when you saw this for the first time. But hopefully feeling familiar now that we're calling a constructor. Making a constructor call, the constructor is assigning values to its instance variables. We're creating an object on the heap with those instance variables, getting those values into those instance variables through the constructor call, which is a method call, so it's a stack frame. The name of the method call is the name of the constructor. That is a method name. Return arrow to where the value is going to be returned to. This is a reference to the node, the object that's being created, the node in this case. I chose 350 just because I felt like 350 was a cool number when I made this slide. And the parameters for the constructor call are also on the stack. Do not forget your parameters. This is a method call. The parameters go on the stack inside that stack frame. Even though they are going to also be over here, they are going to be in memory twice, once in the stack, once in the heap. So hopefully that's all good with everyone. Maybe it was only 2 days ago, so maybe you still have to think about that and study that a little bit more. There's a lot of moving pieces there. Make sure you know all of those for your classes quiz next week. This and the way things references move around in memory. If you have that down pretty good, you're looking pretty good for the classes 1 quiz on Tuesday. And then the stuff that we do today. Honestly, linked lists is a lot of just understanding how references work, and I'll throw a little bit of recursion at you as well. If you're good with all those topics, you might, and this will be common throughout the semester as well, that you might be able to do, like if you're good on all that, everything we've done so far, I could probably give you the linked list quiz right now, and you should be able to do it. There's no new concepts that we're learning with linked list node. It's all applications of concepts and combinations of concepts that we've seen in the previous 3 lectures. So you could probably do like this memory diagram. You could probably do this right now. But of course, I want to show you examples of it. that'll be even more true later in the semester. That everything we learn in terms of memory diagrams, in terms of your quizzes, it's just new combinations of things that you already know, or at least should already know, which is good that it reinforces the concepts throughout the semester. Like that all 6 quizzes kind of reinforce each other, which means learn this stuff. Learn it now, learn it well, and you'll be well served throughout the whole semester. So we hit this constructor call, 1 and null, 1 and null. I chose 350. 350 gets returned to first. And then we hit the next constructor call. This is the part I want to explain a bit because this trips students up quite often. Honestly, it trips students up when they're going too fast. If you slow down and really pick apart what's going on here, I don't think it's too wild. But when you first see something like this, we have first and first twice in the same line, and there's the temptation to think, well, first has the same value in both of those, like it's going to get reassigned, but then that changes what it's going to be over here. That's not quite how it works. How it works is when you have an assignment operator, whatever's on the right hand side of that operator, that expression is evaluated first, and then whatever that evaluates to, after it's completely evaluated down to a single value, then that value is assigned to the variable on the left hand side. So when we get to this line, when we say call this constructor LL node of 2 first, we're going to say, okay, what's the value of first? We're going to go to our stack. First has the value OX350. So inside the stack frame, next is going to get the value OX350. Value is 2. Hopefully that part's not confusing. And then this is going to be a reference to the object that's being created. I chose 250 just out of a hat or out of my brain. 200. Did I say 250? 200. I chose that when I made the slide. You can choose whatever numbers you want. If you want to start with OX1, OX2, hell, even if you don't put the OX, if you just put 1 and 2, I'd be okay with that too. It shows that you understand the concept. I'm not too crazy about the OX. I don't really care about that so much. But as long as you have, the OX means this is a hex value, but I won't do any A through Fs in these just because I think it's a little confusing. But the OX is confusing too, so maybe I should stop doing that. But it lets me know that that value isn't an int for what it's worth. But anyway, so first is 350, so next gets the reference 350. This is a reference to the node that's being created. So when we create this node, those are all the values that we're going to get. We have a node at 200, value is 2, next is 350. The constructor returns a reference to the object that was being created. So this first here is OX350. When this resolves, it resolves to the new object, which is OX200. And then first is assigned the value OX200. It's assigned a reference to the new node that was created. So now after this line executes, first is storing a reference to this new node that was created. It's no longer referring to this node that was created previously. And then we do it again. We create a new linked list node, call the constructor again, 3 and first. First at that point in time was OX200. So next gets OX200. This is whatever number I made up when I was making the slide, 480 in this case. So this is a reference to the new node that's being created. And then a reference to the new node that was just created is what the constructor call resolves to, evaluates to. And then that's what's stored in first. So first now stores the reference OX480. Now notice nowhere on our stack do we have references to the first 2 nodes, but those first 2 nodes are still part of our linked list. So what's stored in memory in a variable that stores a linked list is a reference to the first node of that linked list. So first, I do have another slide on it. So first, let's get to a slide that agrees with what I'm talking about. So first is a reference OX480, just a reference to the first node of the linked list. But using that node, we can follow that node. We can do first dot, get to the nodes, the node that we're referring to. We can ask it for its value and get the value 3. And we can ask it for its next node in the list, OX200. And we can hit that with a dot. If we go dot, we'll follow it to this node. We get the value 2. Ask it for its next. We can say dot, follow it to 350. Get back to our original node, get the value 1. See that next is null, and then know that we're at the end of the list. And then we can stop and say, okay, we've seen the whole list. There's nothing more to do here. Nothing more to see. Cool, right? Linked lists. That was creating a linked list. And notice how the order in which we added the elements is reverse from the order that we actually have in the list. We added them 1, 2, 3, but our list is actually 3, 2, 1. Very common mistake on quizzes if somebody's just, oh, I know linked lists, and they just kind of smash together a memory diagram without actually tracing through the code line by line. They're going to have a list that's 1, 2, 3. And when we do this, actually the next thing we'll see, we'll like print out the list. And then we just look at their in out. If in out says 1, 2, 3, it's a pretty quick fail on the quiz. You got your whole friggin' list backwards. Like, you don't understand this. They just saw 1, 2, 3, wrote 1, 2, 3 here and said, okay, Jesse said there's got to be constructors and objects. Let me draw that stuff into. But they didn't actually trace the code. If they did it completely backwards, which you got to try again. So make sure you're paying attention to the order. This is technically pre-pending to the list. We created a list with the value 1, and then we pre-pended 2 and pre-pended 3, meaning we're adding elements to the beginning of the list, as opposed to appending, which will add elements to the end of the list. Oh, and notice these memory addresses don't have to be in order. These memory addresses are whatever, it's whatever I made up when I made the slides, yes. But they're going to, in reality, be whatever the operating system and the JVM agreed upon and gave us when we said, hey, I need enough space to store a linked list node. And operating system, JVM, we're just going to get some location. We don't care where that location is. We don't know where that location is. We're just going to get enough space that we need. And then we have a reference, and then we link the nodes together using those references, using those directions. This is where you can find the next node in memory. So we're hopping all around memory to be able to link this list together using references. Okay, so let's talk about toString. I mentioned this very briefly last time, partly because I want to use it this lecture. But we're going to write a toString method. This is a topic that we'll talk about in a week on next Thursday when we talk about inheritance. We're actually overriding an inherited method. That's something we don't have to think about quite yet. We're going to give this a toString method. For now, you can just pretend that it's magic. We're going to give this a toString method, which returns a string and is named exactly toString with a capital S. And whatever this method returns will actually be, when we print out the list, if we just said print first, then that's going to call the toString method magically. Like println will call toString on whatever you give it. We're calling toString explicitly here just to make things very, very clear that we're calling toString. But toString would be called kind of magically by println. It's not really magically, but it's a little magically that println also works with primitives though, which don't have a toString method. And we're going to use recursion. So let's use recursion. Let's see another memory diagram. Instead of explaining through this toString method, I just want to show it with a memory diagram. I think memory diagrams are probably the best tool we have to explain recursion, at least at this level, at the intro to recursion level, the first times you're seeing recursion. I think memory diagrams really show it pretty good. It dispels a lot of the magic, because recursion seems like magic otherwise, if you don't see explicitly how it's working. So we're going to call toString. toString is a method call, so we're going to put it on the stack. Even if and I think I'll just avoid this on the quizzes because I've seen too many students fail quizzes over this technicality. It's not really a technicality, but I don't know. It's not something I'm too concerned about you knowing. But if we put print line and then first, like I just mentioned, toString is still called, and you still need to trace that toString call. But if something's in a print line, I've seen too many students just skip in their memory diagram the whole toString, even though it is being called by print line. And they have a fairly valid argument because I always say, oh, I got to move my face. Let me go right here. The only thing in out is going to be the 3, 2, 1. And they have a kind of valid argument because they say, well, Jesse, you always said if it's an internal Java call, we don't trace it. And printline is an internal Java call, so I didn't trace it. And there's not too much I can say to that to counter it. Like, they were paying attention. Like, they listened to what I said and did what I said. But since printline we do know that it will call toString, we still want you tracing that toString. Or else why would we give you the toString code? If this were a quiz, why would we give you the toString code if we don't want you to trace it? If there's any code, there's a general rule of thumb. I think I'll just avoid that this semester. But if we give you the code on a quiz, it's because we want you to trace it. Or else we wouldn't waste our time putting that code on the quiz. So we call toString. toString is going to return into a variable named value. toString is called through first dot toString. So first dot toString, this is the calling object. It's of type LLNode. So we're going to look in the LLNode class for a toString method. And this is going to be a reference to the calling object, which is OX480 in this case. We get to the first line, we're going to create a variable called out, a local variable called out inside the stack frame. Give it the value of the empty string. Immediately replace that value with a new value, out plus equals this dot value. So this dot value, we have 3. And we're going to append that to out. So out is now going to store the value 3. If you're wondering why we have these 2 lines the way we do, and how this works, like this kind of shouldn't work, because this dot value is an int and out is a string, and we're adding them together. Like, do we get addition? Do we get string concatenation? We actually do get string concatenation here. Out is a string, so this is the string concatenation operator, which is overloaded to be able to take an integer as a value. So this does actually work, but if we just did string out equals this dot value, it would not work, because then we're not using the concatenation operator. We don't have that overload effect. We're just using the assignment operator, which is going to say expected string got an int, and it won't do that type conversion. But with this concatenation operator, with that being overloaded, we do get the type conversion from an int into a string. So for what it's worth, if anybody's wondering, that's why we create this in a silly way. We could also do string out equals empty string plus this dot value in one line. But at any rate, this is just kind of a cheesy way to convert our int into a string without having an initial string. So we just initialize the empty string. And then we're going to do our first of many null checks. We're going to see a lot of these this semester. We'll see quite a few of them today, and then we're going to see even more of them when we get to trees, which will be in a week and a half, the following Tuesday, not next Tuesday, but the following Tuesday when we do trees. We're going to see even more null checks. So null, we have null termination of our linked list. So the last node in the linked list next will be null, which is our way of checking if we're at the end of the linked list. So we're going to have that check all over the place. Whenever we have a linked list node, we want to check for null. Either check if the node itself is null, which, well, not in this example, or in this example, we want to check if the next reference is null. Because if next is null, I know that this is the last element in the linked list. So we're taking this element's value, or this node's value, appending it to the string that we're building. And then if we're not at the end of the list, we're going to make a recursive call. But if we are at the end of the list, I don't have any else here. If we're at the end of the list, we're done, and we can just return out. But if we're not at the end of the list, so say I have, I call toString on the last node of a list, it's just going to return 1. It's not going to make any recursive calls. It just returns 1 as a string. And we're out of there. We're done with that method call. If we are not at the end of the list, so if next is not null, we're not at the end of the list, we got some more work to do. So we want to recursively call toString on the next node. And we're doing something a little fancy here with our recursion, in that our recursion, we're going to, our next recursive call needs a reference to the next node, and we're actually passing the reference to the next node through this. So we're calling toString through this dot next. So this in the next stack frame is going to be this dot next. So this dot next dot toString, the next toString call is called through this node, OX200. So when we get that next stack frame, on the stack, this is going to be OX200, and that's how we're moving on to the next node in the list with the next recursive call. Because our recursive call doesn't even take any parameters, so we can't really give it anything. The only way we're moving on to the next node is by updating what the reference to this is going to be, what reference this is going to be storing. So we move on to the next list. We're going to do our same thing, create out with empty string, and immediately replace it with this dot value, which is 2, this dot value 2. So we have the string 2. We're not at the end of the list. This dot next is not null. So we're going to go into our if code block, out plus equals, I don't have to talk about that part yet. And that's going to be a recursive call, this dot next dot toString. So this dot next dot toString, we're at this node when we call toString. So the next stack frame is going to have OX350 as this, because that was the calling object, a reference to the calling object. It's going to do the same thing. It's going to get 1 as a string. But this time, our condition is false. This dot next not equal null is false, because next is null. So it's not null. We got the double negative. We have false for this expression. So we skip the code block and just return 1 as a string. And again, with our recursive calls, I should mention again, our recursive calls, since we're returning to the previous stack frame and not storing it in a variable, we're kind of eventually storing it in out, I suppose, but we're going to have our arrows, or return arrows, point to the previous stack frame. So this stack frame hits the base case, oh, I bit my tongue, our base case of our recursion. We had our base case, which means we're returning without making a recursive call. So that's going to return out, which is the string 1 to the previous stack frame. And now this stack frame got its return value of its recursive call as the string 1. And then it's going to do a little bit of work. It's going to take its out, which is the string 2 at that point in time, append a space, and then add the return value, which was the string 1. Kind of wish I put a comma here. I have these commas separated. And then we're going to return out. That's all we had to do there. Now we're returning out, which is 2 space 1 to the previous stack frame. So now this stack frame is going to get the value 2 space 1. The stack frame is sitting right here waiting for this method call to resolve. This method call resolves to 2 space 1 as a string. It's going to take that return value, prepend empty a space, and then prepend out. Out in this stack frame was the string 3. So we get 3 space 1 space 2 in our out. And that's the final value that we're going to return back to the main method. So value is going to get 3 space 2 space 1, which are all the values of our linked list. So, which we saw before, first is 480, which has 3, a next of 200, which is 2, a next of 350, which is 1, and a next of null. So we expected 321 to be returned from our toString without spaces, apparently. And that is actually what we got through the magic of recursion, with some extra magic of taking advantage of what the reference this is going to be for each stack frame, and making sure that this is going to be updated for each recursive call. And then finally making sure that we prepend it out just to make sure we get the order right as we're going through these. Just the way that we set up our recursion, the values being prepended to the recursive calls is what we needed to get the right order here. And then we print it to the screen. So we print 321 to the screen, and the program ends. And this is about the right complexity that I would expect you to be able to do on the linked list quiz. If I give you something like this, you're able to trace through something that uses a linked list node, builds a linked list, probably of size 3. There's no reason to go beyond 3. With 1 and 2 are their kind of special cases, but 3, if you can do a linked list with 3 elements, you can do a linked list with 100 elements in your memory diagram. So probably 3 elements building a list, and then at least 1 recursive method call, which won't be toString. It'll be something else, something that you haven't seen before, but some recursive call. So it'll be the first time that you trace through recursion. All these topics, like the first 2 lectures, there are a lot of topics that I have to wait for the first quiz to quiz you on. Recursion is going to be one of them that I'm going to hit you with on Data Structures 1. You can pretty well guarantee that Data Structures 1 quiz is going to contain a linked list that's being traversed using recursion. Okay, any questions on linked lists, the structure of a linked list? Will I get the next slide set up? Oh, this is the first, as I'm getting this set up, I'll give a little context to where we are. This is the first, at least in my opinion, lecture, kind of on Tuesday but Tuesday got a little bloated. There's a lot of stuff in there. But this is the first lecture where we're really getting into the 116 content, where the pace of things can start slowing down a little bit, and as we're getting into more complex topics, that things slow down. The first 2 lectures specifically, there's just so much stuff. It's such a rapid pace. Like, here's all of Java. Here's memory diagrams. Here's strong typing. Here's type parameters and generics. Actually, generics we're about to talk about in more depth now. There's just so much stuff. But now the content is going to get more complex, more difficult, but the pace will slow down a little bit. But not a lot. I mean, it's still, the pace is still, you know, we're at the, you know, pedal to the floor for 3 lectures. We're just like a few hairs off of the floor right now. It's still a fast pace, don't get me wrong. It's just not as fast as the first 3 lectures. Okay. I don't see any questions. It's been a while. It's been enough for the delay. Let's keep pressing on. All right. So last time, a full minute ago, we saw linked lists. But there was one big problem with our linked list, is that it only stores ints ever in its entire life. It is a linked list node of ints. Always. Always, always, always. Let's fix that. Let's do something about that. For example, when you want an array list, when you use an array list, you don't create a new array list and just, it's always a particular type. When we created an array list, what we did was specify what type we want that array list to store. We wouldn't just create an array list. We created an array list of integers. We would create an array list of doubles, an array list of strings. Hell, we would create a hash map of strings to integers in task 1. We want to be able to specify these types when we create our data structure. We want that same feature in our linked lists, and we're going to get it, dang it. We're going to get that feature. So let's modify our linked list to not be hard-coded to ints anymore and have our linked list be able to store any type ever asterisk except primitive types. So let's build this same thing that we have an array list into our linked list, and there it is. We're done. So here's all the code. Don't worry, I'm going to go through this in takes about 5 slides for this one. There's a decent amount. And the syntax does trip students up, but there's not a ton to talk about with it. It's one of them things you just got to kind of stare at until you get it. What we have here is a generic. Java calls them generics. I call them type parameters. I think that's what Scala called them, and that makes more sense to me. But I'll use the Java term generics whenever I remember. But these are generic types in Java. So what we do when we create our linked list node class, we don't specify the type. We have what's called, what I call anyway, a type parameter list, which has a variable name, which I chose capital T for my variable name here. And that variable is in place of a type, which will be specified when somebody creates an object of this type. So when somebody creates a new linked list node, they're going to specify what T should be. And you can think of these angle brackets as a type parameter list. I have a type parameter. I'm giving it the type integer. And then for this linked list node that we're creating and storing here, T will effectively be integer in all instances of T. Because I'm saying T, just like val should be 1, I'm giving an argument to the parameter. I'm taking a type argument integer and giving that to the type parameter T, or the Java generic in Java terms. So T is a placeholder or a variable, but it's a placeholder for a type, not a value. So the angle brackets are type parameters, and then in regular parentheses are regular parameters. These are parameters that are values. These are parameters that are types. And I say plural and lists and everything because, for example, in a hash map, you have 2 type parameters. So you have a type parameter list that has 2, one for the keys and one for the values. Here we only have 1, but it's still a parameter list. So I'll still call it a parameter list. It can be comma separated, all the same syntax as you would expect. For a hash map, usually K and V are the variable names. So K comma V is what you would see in a hash map. And I got a bit ahead of my slides here, but I'm okay with that because I think this topic's worth spending some time on and repeating myself a few times here. Now, I chose the variable name T here, which may be a little off-putting, where I have I'm a fan, I haven't talked about this much this semester yet, but I'm a fan of self-commenting code where you give everything meaningful names. If your classes, your variables, your methods, if they all have meaningful names, your code can be what's called self-commenting, where you don't actually have to write comments. Your code just is clear enough that it explains itself. That's always the goal when I write code. I want self-commenting code so everything makes sense just by reading the code. And then I don't have the concern of writing comments. And then the big concern with comments is comments sometimes lie. The compiler is not going to check your comments. So even if you write a really beautiful comment, if you or somebody else goes in later and updates the code but doesn't update the comment, now your comment lies about your code and it's causing more confusion than it's solving. Because comments are just written by people, checked by people, never checked by the computer at all. It's easy for comments to get out of sync with the code. But the code can never be out of sync with the code. So if you have self-commenting code, it will never lie. It will never lie to you. I mean, I suppose you could just choose really stupid names that lie, but at that point, your code's not self-commenting. So why am I choosing a single letter variable name here? Sounds silly. It seems silly. And the answer is convention. This is just how type parameters roll. If you see a single letter, a single capital letter just out on its own, that's a signal to you and all other developers across the whole world that that's a type parameter. That's a generic type. If you see capital T, capital A, capital K, capital V are some of the common ones. A, B, K, and V, as I mentioned, for hash maps for key and value. Pretty clear, K and V. As long as you understand that a single letter is a type parameter. If it's a K, it's the key. If it's a V, that's the value. T for type in this case. A, just because sometimes we like to start with the first letter. There's another common one. I'm blanking on it right now, though. So convention, that's why I have a single uppercase character as my variable name. And it's understood that that's a type parameter. So we see these capital T's all over. It's a type parameter. T for type. But it could be... Oop, I did get ahead of my slide. I should have clicked one more time. Oh, no, I didn't. And whenever you need a value of that type, you use capital T in place of that type. So in the constructor, if this is a linked list of some type T, then the constructor takes a variable of type T. And we're going to store a variable of type T in our instance variable. So when we write this code, we actually don't know what the type of value is going to be. It's just going to be whatever the user wants to store. Whatever they said T should be, integer in our example here, T is going to be integer. If somebody wants to create a linked list node of player objects, they can specify player here, and then T will be player and will have an instance variable of type player. But the type depends on whatever the user wants to store. And we can also forward this as the type parameter in other objects. So we also want a linked list node of T. So in our linked list node of T, we're going to refer to a linked list node of T. We kind of just forward that type parameter to the next node in the linked list. And then when we specify what that type parameter is, we have a type parameter list. And we can optionally put integer here, as I mentioned a few lectures ago. I think both lectures. This might be the third lecture in a row that I mentioned it. I don't remember. But we could also put integer right here. But it is optional in Java. Java's going to figure out that we mean integer there, so we don't specify it. I should add it. I mentioned this before, but I should add it in my examples just to be more explicit about what's going on. But we do have integer here. Java's just figuring it out that we're storing in a variable of type integer, that this is also going to be integer in this type argument list. So since we specify integer, all the T's are effectively integer in this example. So you could read the code as integer, 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 integer. For this example, if I created another linked list node after this in the same code but specified string, then this would be string, 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 string for that linked list node object. This type parameter can be different on a per object basis, which is why the class doesn't tell you what T has to be. But each object that we create is going to have a specific value, a specific type for T. So if I said, I want to make strings instead, I put string here, and then all the T's become strings. The code, and I've had students get tripped up on this before, the code doesn't change. Nothing about the code changes, but T is effectively string. But the code won't change. And don't put string here. I've seen that before too. I have, if my homework assignment says create a linked list node of ratings, and I'll see public class linked list node of rating, and then rating for all these instead of T, which works, but rating is your variable name, and then you have to also specify rating when you create that linked list, and it just gets confusing. And speaking of self-commenting, that's like self-uncommenting code. It's really confusing to read because the student's confused, and then I have to explain things in office hours, and everything's fine. But yeah, this you can just leave as T, and you specify the actual type when you start using objects of that type. And this gives us what we want. Our linked list node can be used with any type, just like ArrayList, just like HashMap. So that's generics. That's generics in not too much time, about 10 minutes. So we're going to start using generics all over the place. So it's worth thinking. Worth thinking about for a second. Making sure you got this down. So we have a type parameter list, just like we say array list of string, and then the array list code. When we actually did have the array list code up last lecture. These type parameters were there, and I said, don't worry about that. We'll talk about that on Thursday. Well, it's Thursday. We're talking about it. But the array list class does have the same syntax. It's public class array list of, it might be T. I forgot what letter they use, but capital T, capital A, whatever it is. Capital V maybe. Whatever, capital E. It might be capital E for element. But it's a single uppercase capital letter. Single uppercase letter for the variable name. And then when we say array list of string, that value is effectively string throughout the array list code. Right. There are no questions about generics. Y'all are pretty quiet today, which is fine. As long as there are actually no questions. I always get nervous when a class is quiet because top chat versus live. I had top chat on. Some messages such as potential spam may not be visible. I want everything visible. I'll filter out the spam. It's not like chat's going crazy. And I want the timestamps on. 12:08. Oh, so that actually did just came in. So that message popped up right when I changed that setting. So I thought it marked your message as spam. Alright. Well, and I don't want this here. It wants me to heart your comment. You know what? I'll do it. No, it wants me to sign in. I don't want to do that. Oh no, I'm messing everything up. Hold on, Chad. I lost the chat window. Chat. There we go. Okay. But I got this heart like covering up part of the chat. I don't know what I clicked. I turned on timestamps, but why would that be part of it? Anyway, I'll just read around the heart if I can. Why do we have to write linked list node with empty angle brackets after new if we already specified that it's a linked list? It's part of Java syntax. So Java used to, is my short answer, it's part of Java syntax. Java used to force you to specify the type here, which made sense. When you create a new linked list node, you have to set what T is going to be when you create the linked list node, and you also have to set that for the variable. So a variable can't just store a linked list node. It actually can, but you'll get all kinds of errors. A linked list node, you don't just create a linked list node variable. You say, I want to create a variable that stores a linked list node of strings. Any linked list node where the type parameter is string, and then you create a new linked list node with the type parameter of string. But with an update, it's been a long time now, but with one of the updates to Java, they decided, you know what, you don't have to type string twice. We're going to make this optional, but we're still going to make you type the angle brackets. You can just leave the argument list empty, though, the type argument list. I don't know why. I'm sure there's a good reason why that's the case. But they don't make us type out the whole type twice, which I honestly actually wish they would for educational purposes, but it's optional to put the types, but not optional to leave off the angle brackets. So again, my short answer is just the way Java works. Java syntax. It's so weird. I got this icon covering up messages. I don't know how to get rid of it. Computers are tricky. All right, so let's start using our linked list. So we have a linked list and we've navigated it. We printed the values to the screen. Yay, go us. But let's start seeing some more advanced things to do. I say advanced as I have getters and setters on the screen, but we'll get to some more interesting things that we would want to do with our data structure besides just printing it to the screen. So first, we're going to need some getters and setters just to get the job done, because we have private instance variables. That's fine as long as our code is inside the linked list node class, which honestly a lot of it today will be. But let's set up our getters and setters. And here's an example of where getters and setters give us some more control over our code, over our classes, over our objects, is that I don't want anybody changing the value of our nodes. Not necessarily a bad thing to allow that, but I'm just not going to allow it because it would break some of our... Actually, would it break any of the ones today? I don't know. I'm just not going to let people change the values. So I'm just not going to give them a setter. I'm just not going to give people a set value method. We can get value, we can set next and get next, but we're not going to let them change the values of our linked list nodes. That'll be more important when we talk about binary search trees, but I guess it's not really important right now. But I'll set that seed of the idea that we can use getters and setters, or the lack thereof, to control our instance variables. All right, and now let's get into the more complex stuff. Not overly complex, we're not throwing too much at you, but things that you would want to do with a data structure: ask it for its size. Hey, linked list, how many elements you got? Append a value to the end. So we effectively did prepend before. We didn't write a prepend method, but we were effectively prepending to the list. But what if we want to append, which is a more common use case? Usually you want to add elements to the end of a data structure instead of the front. So let's write that method for append. Find, given a specific value, tell me which node stores that value. With linked lists, it's often important to actually have the node that you're looking for, not just is this value in the list, true or false, but if this value is in the list, can you tell me which node? Give me a reference to the node that stores that value. In case we want to do something to the linked list, we want to be at that location in the linked list. And then min, this will be a lot different structure than the other ones, but finding the min in a linked list of doubles specifically. And the reason we have this min, and the reason why I'm going to say this is the most important one in your lives right now, is because it's made to parallel programming task 3. So min is going to be very similar to some of the things you'll want to do in programming task 3. It'll have the same structure, the same setup, the same idea. As an example, using doubles, and then for your homework, for your programming task, you'll create a linked list of ratings, of rating objects, and then follow similar structure to this. So I want to make sure I have an example that shows you, hey, here's another way we can use a linked list. The big difference is these ones are all going to be inside the linked list node class, which gives us a big advantage in that in our recursion, we can pass a reference to the next node through this. We can use take advantage of the reference stored in this to be able to get the job done, and we won't do that in min. So we're going to see how to pass a reference to the next node to the next recursion without leveraging this. So we're going to see two different ways of handling recursion with objects when we need to navigate through different objects by reference. And hopefully that'll make a lot more sense when we get through these. So let's just do it. And I'm going to have what I call abbreviated memory diagrams in these. I'm not going to have time to go through every full memory diagram. So I'm going to have just illustrations that'll have the same content as what the memory diagram would have, but in a much more almost oversimplified way. And then hopefully you can leverage the string example to be able to understand what the memory diagrams would look like. And it also gives you good practice. If you want to know what those look like, write a memory diagram for this example. It'd be really good practice for the quiz on Tuesday. So for size, let's start with size. We're inside the linked list node class. I removed the constructor just for space on the slide, but it is still there. And then size, define the size of a linked list. we're going to say if next is null. So if this is the last element in a linked list, then it's going to say, well, the size is 1, because that's how many elements, how many nodes that node knows about. For all it knows, the last node in a linked list doesn't know anything about the previous nodes. For those of you who know, we're doing singly linked lists only in 116. But there is something called a doubly linked list where each node knows its next node and its previous node, and there's different things you can do with that extra information. We're using singly linked lists, so each node doesn't know anything about what comes before it. So the last node in a linked list, it could be a linked list of 1,000,000 elements, but to the last element in that linked list, for all it knows, it could be the only element in that linked list. It just has no idea that there are other nodes that even refer to it. For all it knows, its reference could be right on the stack in the main method. It could be the head of the linked list. I didn't introduce that term yet. The first element, the first node in a linked list, we often call the head of the linked list. So it could be the head of the linked list for all it knows. It doesn't know it has 999, why'd I start this one? 999,999 nodes that come before it, where the second to last one of those nodes refers to that node and it's the end of the linked list. It doesn't know. So when we ask it for its size, it's like, well, next is null. I don't know anything about what comes before me, so as far as I care, I'm a linked list of size 1. It's just going to return 1. So that's our base case, which for recursion with linked lists, the base case is often the last node in the list. And if we're not at the last node of the list, we're going to ask the next node, hey, what's your size? It's going to return some number, all of the nodes that it knows, how many nodes it knows about. Then we're going to bump that up by 1 and return that. What's T? I might need a more specific question than that. I spent like 15 minutes talking about what T is. Do you have a more specific question? It's the type parameter is the short answer. If you have a more specific question, I can give you more a better answer. But T is the type parameter. In this example, T could be anything. Actually, we're about to see an actual T. It's going to be ints in my example, integer. But it doesn't matter for understanding how the size method works. So if we're at the last node, that node says, I'm of size 1. If we're not, each node is going to ask the next node, hey, what's your size? And then add 1 to that, and then return that. T is used to create one linked list node class that can be used to store any type. Just like there's one array list class, but you can use it to store doubles, integers, strings, players, ratings, anything that you want. T is what allows us to do that. The generic type allows us to create a linked list node that stores any type. So visually, in my abbreviated memory diagram, barely even resembles a memory diagram, actually. Probably shouldn't even call it that. But the caller, whoever's calling the size method, is going to say, hey, list. I have a reference to the head of a list. How big are you? How many elements you got? How many elements you got here? And this node is going to check next. It's going to see that it's not null. So it's going to say, well, hold on. Let me get back to you. I got to ask, I asked my buddy about this. It's going to ask the next node on the list and say, hey, how many nodes are there after me? Like, I'll account for mine. Don't worry about me. But starting with you, how many nodes are there in this list? How many nodes are there in this thing? And it's going to say, well, my next isn't null, so I got to go ask somebody about this. So let's say, hold on. In each hold on, this is going to be another recursive call. We're going to get another recursive call where this node is going to say, yo, no. How many values you got? How many values are after me? I'll account for me. Don't worry about me. But how many values starting with you are there? And it's going to say, well, hold on. And it's going to say, well, okay. Let me think about this one. My next is null, so I don't have anybody to ask. So I better give this, I better give this other node an answer because he really wants an answer. Next is null. Well, I'm 1, so I'm just going to return 1. I must be the end of the list. Whoever's asking me, I don't know who's asking me. It could be the original caller itself. It doesn't know. It doesn't care. It's just going to see null and return 1. So this node's going to be like, yo, just one. Just got one node here. This node says, all right, cool. Well, if I refer to a node, like everything after me is just one node, and I'm one node, well, I'm just going to bump that up by one and tell this dude who's asking me, this node who's asking me, I'm going to say, well, two nodes. We got two here. So two nodes. This node's going to be like, okay, so everything after me is two nodes. There's two nodes after me. I'm going to bump that up by one. 3 must be how many nodes, including myself, are in this list. If I am the head of the list, it's going to say 3. It doesn't know if that was a recursive call being made to it. It doesn't know if there's a million elements in this list. Or in this case, it was the original caller who actually wanted to know the whole size of the list, and this is the head of the list, but it doesn't know that. It's going to say 3. The original caller says, all right, I got my answer. Cool, thanks, bye. So that's how this recursion is working. Every node is accounting for itself, and we're just adding one, adding one, adding one through each recursive call. Each recursive call is just going to add 1 to the total. And if every node either returns 1 or adds 1, the original node is going to give the entire size of the entire linked list. Yes, we can get a Stack Overflow. So this isn't the best way to do things, I'll say. That we can get a Stack Overflow. So if we have so many nodes that we run out of stack space with all the recursive calls, we get a Stack Overflow, program crashes, everything's lights on fire, it's bad. There are ways to get around that. One, we could actually just use a loop. I didn't mention this yet, so I might as well mention it now, because I need to by the time we hit the end of this lecture, is that a lot of these methods that we're seeing with linked lists, hell, I'll even say all of them, could easily be written with loops instead of recursion. And we would write a loop, and that would get rid of the potential of overflowing the stack in this case. I'm going to use recursion for all of the linked list node algorithms because it's going to give you good practice with recursion. And then when we get to trees, you pretty much can't use loops when it comes to trees. You're going to, I'll say it this way, you're going to want to use recursion when we get to trees. Yeah, a lot of students like to resist learning recursion. They resist using it because it's complicated. It's this new thing. It's tough to understand. When we get to trees, you're going to see why recursion is going to save us a lot of time and effort, because writing tree algorithms with loops is difficult, to say the least. When we get there, I'll throw down the gauntlet and challenge you all to rewrite any of the tree algorithms without using recursion. And a few students have taken me up on that, and their code is way more complicated than the recursive code. But a few students have done it as a challenge, as a fun exercise. So I recommend that you try it if you're a non-believer in recursion, especially. Just try it. Just try not using recursion. That's not true with linked lists. Linked lists are, the recursive code and the loop code is about as complex. It's about the same. But I'm going to use recursion just to give you practice with it. So that'd be one way of getting rid of I'm getting ahead of myself there. One way of getting rid of the Stack Overflow issue. The other one is tail recursion. If we rewrite this method so that the recursive call is the last thing that the recursion does, that the method does, then the compiler, the JVM, it's going to reuse stack frames and not add a new stack frame for every method call, because there's no point in having a million stack frames. Well, you wouldn't fit a million in your stack anyway. 100 stack frames where each stack frame is just sitting there waiting to return whatever it gets as a return value. So it actually squashes that down into a single stack frame. And if we do that, then we can have a recursive method that doesn't have the concern of overflowing the stack. Tail recursion, I'll mention a few times throughout this semester because I think it's fun. It's a fun topic. But it's not something that I'll require you to know about. So when I say tail recursion, if you just want to cover your ears and pretend I didn't say it, it's fine. Just make sure you're listening by the time I get back to the content I do need you to understand, which is right now. So, talking about append. Our next method that we're going to see, append to the end of a linked list. This is a little more complicated than prepending. With prepend, we had a reference to the first element of the linked list. And, oh, sorry, I didn't read this question yet. How do you remove a node from a linked list if the nodes don't know what comes before them? So the nodes don't know what comes before them, but you know what comes before them. So you have to work with your references in a way that you're going to remember that. And that question is the ultimate question of task 3. The pinnacle difficulty in task 3 is removing a node from a linked list. I don't think task 3 is too hard, except for that last thing where it has like 80% at least of the difficulty of the entire task, removing a node. And what you need, and I won't show you the code for removing a node because it's your homework assignment, but I'll go over the theory. We'll get there in probably about half an hour. I'll show you the theory, but I'll give the overview of it right now. Is that you need a reference to the node that comes before the node that you want to delete. And then with the node before the node, if you have references to both, so you need a reference to the node you're going to delete because you need to know, you have to check, is this the one I want to delete? If it is, you need to also have a reference to the node that comes before it, but you have to keep track of that. You can't ask the node what comes before it. You need to keep track of that in your code. And then with the node that comes before it, you can remove that node from the list by updating its next to its next. And then your homework, when you really get into it, when you start coding on that one, the real question comes in. That I think that is a lot of the difficulty too. But then what happens when the node you need to delete is the last node of the list, and what happens when the node you need to delete is the first node of the list? Those are two special edge cases that I expect you to test for and I expect you to have the code for. Kind of putting together everything that we've seen so far. That'll be classes, linked lists, and testing, all combined into one nice programming task objective. One method in a programming task. Which lets it test so much stuff. That's one of the first things that students will struggle on is deleting a node from a linked list in task 3. And just to give you a heads up, from task 3 to task 4, there is a jump up in difficulty. I think that method that I just mentioned in task 3 is your first the first tough challenge of the course, of the programming tasks. And then task 4 onward, it's just a lot of difficulty moving forward. A lot of it will be at that difficulty level. So don't get too overconfident if you breeze through task 1 and task 2 in the first half of task 3. That's kind of your sort of gentle entry into the course. So just a heads up on what's coming up. If you're struggling already and you haven't even gotten to the end of task 3, there's not a lot of weeks in this semester. You really gotta, I don't know. It's a tough semester in 6 weeks. All right, so when we're appending, prepending was kind of easy. We already had a reference to the first thing, but appending, and a lot of that was stuff I wanted to talk about, by the way. So that wasn't even a sidetrack. It's just when I get to those slides, I'll breeze through them a little faster. When we want to append, the first thing we have to do is find the end of the linked list. The only thing we have is a reference to the first element, the first node in a linked list. So if we want to append, the first task is to find the end of the linked list, and then we can actually append. So find the end of the linked list, and then append. So our append method, we want to append a new value. So we're going to check, is this the last node in the list? Is next equal to null? If next is null, this is the last node of the list. And if we're at the end of the list already, this dot next, instead of being null, we're going to overwrite that with a new linked list node that's going to have the value we're appending and next of null, because that new node that we just appended is now the end of the linked list. So its next has to be null. If next is not null, if we're not at the end of the list, recursively call append on the next node. So go down the list, ask the next node, hey, this needs to be added. And keep going down, passing the buck, as it were, down the linked list until the last node says, oh, I'm the last node. I know where to put this value. So if we want to add a value to this linked list, we're going to tell the head of the linked list. We're going to say, hey, add this thing. It's going to say, yeah, no problem. And it sees that it's not the end of the list, so it's going to tell its next node, hey, we need to add this node. The next node says, sure. It's going to see that it's the end of the list. So since it's the end of the list, it knows what to do. It's the node that has to do the work. So it's actually going to add that node by replacing its null with a new node that refers to null and contains the value that was going to be appended. And then the way this method is written, it returns void. It just kind of ends. There's no feedback to the caller. So we don't actually get feedback or confirmation that that value was appended. We just have to trust our method and say, you know what, I called append. I'm pretty sure that value is going to be in there, which is true in like if you add to an array list, for example, you don't get any feedback. There's no return value or anything. You just call add and you assume that it worked. So we get no feedback for the caller in this case. All right, moving on to find. So find, a little bit different. In this case, we have two base cases to our recursion. Only one of these conditions will make a recursive call. And we have two base cases. One, did we find the value we're looking for? If we did, we want to return a reference to the node containing that value. So we're going to return this. This is exactly, if this dot value is equal to the value we're looking for, then this is a reference to the node that we're looking for, and we're going to return that. Else if, so if this node doesn't contain the value we're looking for, and this dot next is null, meaning we're at the end of the linked list, then we're going to return null. This is what our method's going to do if the value is not found. Since we're returning a reference, if the value is not in the linked list at all, we're going to return null to indicate that. So whoever's calling this method is going to get the return value and say, if this return value is null, then I run my code that says this value is not in the linked list, you know, do whatever it needs to do. Else the value was found, and I'm holding a reference to a node that contains that value. And this find method, for what it's worth, is going to return the first node that contains this value. So if we have this value multiple times in the linked list, we're going to get the first node that contains it as our return value. Else, if in either of these two cases, if this node doesn't contain the value and it's not the last node, then we make our recursive call and just move down the list. So somebody calls find and says, hey, I want to find the value 3. First node says, all right, let me check. Okay, I don't have 3, so I'm going to ask the next node. This node says, okay, let me check. Well, I have 3. My value is 3, so it's going to hit this first base case, not make a recursive call, return. This node gets its recursive call, its recursive call's return value, which is a reference to this node. And then it can tell the caller, hey, that node over there has the value 3, and it's going to return a reference of that value. This node returns itself. This is a reference to the calling node. And then this returns that reference to the original caller, a reference to this node. So it says, hey, here's a reference to the first node that contains the value you were looking for. If the user asks for a value that's not in the list, they're going to ask for 8 this time. This node's going to say, well, I don't have 8. Yo, you got 8? Hold on, let me check. I don't have 8. Do you have 8? Hold on, let me check. Well, I don't have 8. And next is null, so we're going to hit this base case to our recursion. Return null. Return null. Just returning whatever the recursive call gives us. By the way, this is an example of tail recursion, as a side note. Gonna return null because the recursive call is the return value of the recursive call. There's nothing left to do after this returns. We're just returning what's returned. So there's no point in preserving that stack frame because it's done doing all of its work. Returns null, and the user gets the bad news that whatever they're looking for is not in this list. Okay. So that's our 3 algorithms that we're putting in the linked list node class. The next one is what I that is the most important one, at least in terms of programming task 3. And I want to explain why. So the bigger question is, why did find work? And why isn't min going to work the same way? So in our find method, I snuck in this dot equals method, which is a little coy, a little sneaky thing, that I snuck in this dot equals method, which actually works even though we don't know the type of value. The value could be any type T. Any type in Java, even any type that we don't even know exists yet because somebody hasn't written that class yet. Some class that you're going to write a year from now, this linked list node can take that as its value for T, when we'd have no idea what that value is going to look like. Yeah, we're calling a method on it. We're calling dot equals method. How do we know what that class you're going to write a year from now is going to have a dot equals method? Well, we actually do. We actually know that it will, because it has to, because every single type in Java, except primitives, has a dot equals method. Every single one of them. You can't have a type, a non-primitive type in Java, which, since type parameters can't take primitive types, this has to be a non-primitive type. It has to have an equals, so we can safely assume that a dot equals method exists. So it's a little sneaky that I use that, because we have a really strange assumption that equals exists in every method. But what about min? How are we going to do the same thing for min? Same with toString. ToString and equals are the two that we'll see that exist in every single class. There are a few others like hashcode, but those are the two we'll see, ToString and equals. Every single type has them except your primitives. But what if we need to use something that doesn't exist in every single type ever? Like min. Like when we want to find the min, we're going to use the less than operator. But every class, every type doesn't have a less than operator. This is specific to numeric types to have this less than operator. So we can't put less than here. If we do this dot value less than value, it's going to be a type error, because type T of any Java type ever, every single Java type in the world, even those that don't exist yet, certainly do not have a less than operator associated with them. So we can't use it. So what do we do? Specifically, for those of you who read ahead with task 3, you're going to need a linked list of ratings, and you'll have to find a rating. You'll have a linked list of ratings where rating is a class that has a numeric rating from 1 to 5 as an integer, and also a reviewer ID, which is the ID of the reviewer who made that rating. And you'll have a linked list of these ratings, and you'll be given a reviewer ID, and you want to check, did the reviewer with this ID make any ratings that exist in this linked list? So you want to navigate through your linked list of ratings and check if any of them have that reviewer ID, and if they do, if any of them do, you return true. If you get to null and none of them do, you return false. So that's one of your first linked list tasks, is to write this. Did this reviewer rate this song? Is what is the theming that it's going to be. So we need to take a reference. T will be a reference to an object of type rating, and we need to call its getReviewerID method. And none of that's going to exist in a generic type T. None of that's going to exist. It's not toString. It's not equals. We're completely out to lunch on that one. So let's take a look at how to do this with less than and doubles with the min method. And then hopefully in your homework, you can see the parallels to how that applies to checking if this reviewer made a rating in this linked list of ratings. Okay, and here it is. There's how you do it. Problem solved. Good lecture, everyone. All right, for this, of course, joking, but I'm hilarious. We want to create a new class here, linked list of doubles, which is going to be a very simple class. It's just going to contain a linked list of doubles. That's its whole purpose, is to just store this linked list of doubles and have some functionality, mainly the min method that we're interested in, that's going to work with those doubles. To go with the parallel, this class is going to be your song class. Your song class is going to have an instance variable that's a linked list node of ratings. So this structure, if instead of linked list of doubles, this said song and linked list node of ratings, this is going to parallel your task 3 quite nicely, of course, by design. So let's talk about how this works and what this is. So first, the add double method. This is just append. That's all I have to say about that, isn't it? So this is just append. The linked list node class has an append method, so we just want to call its append method. We're not going to rewrite append. There's no point in doing extra work that you don't need to do. I gave you that code for append in lecture. It's in the examples repo. That means it's fair game to just straight up use in your homework. You can just use the append method that we just talked about. You can cut and paste that code. It's already in the homework repo, I believe. I don't think I pulled the append method out of that linked list node class that's in the data structures package. It's already there. You just call append. The only caveat here is that if your linked list is empty, then this variable here is going to have a reference to null. It's just straight up empty. So if that's null, you have to make sure you initialize the list, create your first linked list node. And as much as you might be tempted to, I don't know why I see this so much. I guess there's just too much nulls going around that it gets confusing. Do not do this. I'll see some of you will do it anyway. We'll skip this part of lecture, whatever. I don't know what you do. It's 2.5 hours per, twice a week, so it's easy to miss one thing, I suppose. But don't do new linked list node of null. There's never a reason, at least in this class, there's never a reason to do that. There's never a reason to have your value be null. This should never, ever, ever be null in CSE116. That would be a linked list. If you create a new linked list node of null, what you have is a linked list of size 1 that stores one element, and that element itself is the value null, which isn't what you want. Not in this class. We don't do anything remotely close to that in this class. And students do that trying to create an empty linked list. You don't have an empty linked list. You have a linked list with one element where that element is the literal value null, a null reference. And you get null pointer exceptions all over the place when you do that. And everything's broken, as it should be. If you want an empty linked list, this is how you do it. Have your variable itself just be a reference to null. That's an empty linked list. It's just nothing. And then since that can be null, we have to have more null checks. If the linked list doesn't exist, if it's an empty linked list, make it a linked list of size 1 with the value d, because that's the value we're adding. If it's not null, then we can leverage the append method and just call append. And that's going to append that value to the end of the list. Your song class should pretty much have this cut and pasted. I should not have any questions about how to add a rating to a song until you get to checking if a reviewer added a rating. Then it gets a little bit more, but not too much. Like I said, it's the deleting from the list. By the way, the delete method, since we have some of the flavor out there, the delete method is deleting a rating by reviewer ID. So here's a reviewer ID. If this reviewer has rated this song, remove that rating from the list. All right, now let's talk about the min method. How do we do min? Well, first, if the list is empty, we have to have null checks. Since numbers can be null, we always have to check for that, or else we're going to get null pointer exceptions whenever we say this dot numbers dot. That's going to be an error. So we have to check if it's null. If it's null, we're just going to return something. I chose negative 1.0 as some default value. I don't know if that completely makes sense in this context, but we would, because negative 1.0 could actually be the minimum value in the list, so it doesn't fully indicate. But we want something to indicate that there was an error here, that the list was empty, something went wrong. I chose negative 1. It doesn't make sense in this context, but whatever. I just wanted to return something. But if the list is not empty, then we actually want to find the min value in this linked list. So to do that, we need to know what node we're currently considering. What node are we currently looking at? We had to do this with the find method too. We needed a reference to the node we're considering so we can check that node's value and then check that node's next if it didn't have the value that we're looking for. The reason, and what we did there is used this, made the recursive call through the next node, and then leveraged this. And the reason we could do that is because we were inside the linked list node class. But at this point, we're outside of the linked list node class. We're in linked list of doubles, or in your homework, you're going to be in the song class. You don't have access to a linked list node through this. Through this, we have a reference to linked list of doubles, which has the head of the linked list, but it doesn't tell us any information about which node of the linked list we're currently considering or which nodes we've already considered. It doesn't give us any extra information about where we are in the linked list. Where before we could do this dot, we could do it that way because we were calling the method through a reference, through an object of type linked list node. So this was a reference to a linked list node that was part of the linked list. It's no longer the case. So we need some way to keep track of which node we're considering, which node we're currently looking at, that we're going to do our comparison to see if it's the min value. So to do that, we would like to do that with a parameter. Parameter is a good way to pass information to a method call. No, like that's how we do it. To pass values to a method call, we use parameters and arguments. We give it arguments, those become the values of the parameters, and then we have a reference to the node if we have a method that takes a linked list node reference as one of its parameters. But the min method doesn't take any parameters. So what are we going to do? We're going to write a helper method. I want a helper method that's going to tell me which node I'm currently. Oh, I got ahead of my slides again. I do that a lot. Which node we're currently looking at, which node are we considering, and we want another piece of information too when we're going through min. Like thinking about if you're writing a loop to find the min value, there's two things you want to know. Which value am I currently considering, and what's the best value I've seen so far? So we're going to make those both parameters to our helper method, the node that we're currently considering, and what's the minimum value that we've seen so far. And then we're going to call that helper method. To initialize, to make our initial call, we're going to call it with this.numbers, the head of the list. We're going to consider the first node in the list first. And integer.maxValue, this is the largest value that an integer could possibly represent. So once we get to the very first node of our list, that's going to be overwritten by whatever value is in the first node of the list. So max value is a constant. It's the largest value that can be stored in an integer. So if we're finding min, initializing our min to the max value ensures that it's going to be overwritten. Either it's overwritten or the linked list node actually only contains the max value of an integer. Either way, it's going to give us the right answer. And we've already handled the case where our list is empty is going to return something different. So this is a safe initial value for our min. And so this is the method that we want to call. This is the one we're going to use specifically because we're setting up recursion. By the way, I didn't mention that point yet. We're setting up recursion, so we need to pass the values, the partial work that's been done so far. We need to pass that to the next recursive call. And the only way we can get information in the next recursive call is one through the reference this, like we leveraged before, but this, it's going to be a reference to the same linked list of doubles every time. So that's not helpful in this case. So our other option is through the parameter list. So we want to make sure our parameters have all of the partial information that each recursive call needs to be able to get its job done. That's the node that it's considering, that it's in charge of checking, and the min value that's been found so far. But we don't want whoever's calling the min. Like if you have a linked list of doubles, or if you have a song and you want to find if a reviewer rated something, you don't want to have to give these parameters. Like, these parameters are specifically in implementation detail because we're setting up our recursion. If you have a linked list of doubles and you want to ask it for its min value, you do not want to care about this stuff at all. You don't want to know that this should be initialized to the head of the linked list, which I don't even have a getter for, so you can't even do that. And you don't want to worry about this integer.max value stuff. You don't want to worry about any of that. You want to say, yo, linked list, what's your min value? No arguments. And then have that method call the helper method, which the caller does not have access to because it doesn't need to. You don't want to care about this. You don't need to care about this. This is the public API, the public interface. They call min with the no parameter version, and then that forwards the information, forwards the call to its helper with the initial parameters that are needed for the recursion, but as a private method because nobody outside this class, this method only exists so min can call it. So nobody outside this class needs to know that this even exists. Nobody cares how we wrote the code for min. They just want to know that min works and it does its job. This is encapsulation. I've been trying to use that word more often. I had a TA got asked about encapsulation during an interview, which they knew all about encapsulation, but I never used the word encapsulation. So encapsulation is the idea of hiding details. So whenever we have something like this, this method is encapsulated. This instance variable is encapsulated because we're hiding the details from whoever's using our code. Whoever's consuming our code only knows about the public methods. Everything else is encapsulated. Hiding the details. Very, very powerful, very important concept to organize code, mostly. Makes code easier to use, easier to understand. Good. It's a good teamwork habit to get into. And then each recursive call is going to do its work. This is the same thing we would do inside a loop, except we have recursive calls. So the main comparison that we want to do, if this node's value is less than the min value, we found a new minimum. We got a new minimum value. So when we make the recursive call to the next node, we're going to pass it this node's value as the new min for the next recursive call. If this node's value is not less than min, we're going to make the recursive call with the old min because we didn't gain any new information by checking this node's value. Nothing changed. We're just go on to the next node with the same min. And when we get to the end of the list, if node is null, notice that we're not doing if node.next or node.getNext is null. And we have to use our getters and setters here, by the way, because we're outside of the linked list node class. So we can only access the public methods of linked list node at this point. So getters in this case. I guess we didn't use a setter yet. If we're at the end of the list, so if node is null, just return whatever the min is at that point. Because if we reach the end of the list and min is the minimum value out of all the nodes we've already checked, then we've already checked all the nodes and min is actually the min of all the values. Do not do node.getNext equal null in this case. You have to be careful. It's different depending on how you set up your code. Before it was if node.next equals null. Now it's node equals null. When to use each one, you have to think through the logic of your code to know which one to use. Because in this case, if we get to a recursive call and we say if node.getNext equal null, return min. When we get to that recursive call, like, guess what we've done? When we do this check, you know what we've done with the node, before that? Nothing. Nothing at all. We've done nothing at all with that node. So what if the last node of the list contains the minimum value of that list? What if the last rating in your linked list of ratings was a rating made by the reviewer that you're looking up? Make sure you're checking the last node. There's a very common mistake. I'll see it in office hours in Piazza. What if the last node in the linked list is the one that contains the interesting value? You want to make sure you're checking every node, including the last one. So if we did node.next, we would never check that node because we're doing all of the checks for a node after the null check. In our other examples, we were doing the checks for that node before the null check. So that's the big difference here. And actually, if I can, oh, yeah, right here. So here in our find method, we're checking the node's value to see if it's equal to the one we're looking for before we're checking if next is null. So we're checking its value, processing that node, and then checking if it's the last node. So that's why we did this.next, because we already processed the node before the null check. If we swapped these and we said if this.next equals null, else if this.value equals value, that's wrong. Because if the value we're trying to find is the last node of the list, we're never going to find it. We're never going to check it, because we said if this.next is null, we're done, but we've never processed this node. We never processed the last node in the linked list. So make sure you're thinking through your logic when you're writing your code with linked lists. Make sure you're checking that last node. Make sure that node is being checked. So here it's node equals null because we're processing after the null check. So once we're past the end of the list, so we actually got to the end of the list, processed the last node, did node.getNext, which returned null, made a recursive call with null as the input, and if that ever happens, that means we've gone beyond the end of the list, which means we're done. We've already processed the entire list, and we can just return min. Which, I was going to say, I'm pretty sure is my last slide here. Ooh. We're a little behind on time. Means I'll be watching for questions still. If you have questions, let me know, but I ain't got time to stop. So there are a few slides at the end of that slide deck, but I have them duplicated in the next one, plus an extra slide. So I want to talk about deleting a node with these slides, just because I have a little extra information in these ones. Deleting a node. Because that lecture, as a weekly lecture, the last one went over, and I had to put these slides on the next one. And it's super important for your homework, so I can't just not explain delete a node. So delete a node, I'm not going to explain in very much detail. Again, that's what you're tasked to do in your homework in programming task 3. So I'm not going to give you the code and just have you run the code. That's silly. I want you to get your hands on a linked list and show me that you know how to work with them. Show me that you understand all this stuff and can write code related to it. So what if we want to delete a node? How do we do it? But I'll still show you the concept of what deleting a node looks like. So what if we want to delete this node containing the value 2? And I mentioned this a bit earlier, so I'll go through this a little quick. But we want to delete the node with the value 2. What we need is a reference to the node that comes before the node we want to delete. So when we're iterating over our list looking for a value, we need references to 2 separate nodes in memory simultaneously. One, the node that we're going to check for the value we want to remove, and the other is going to be the node that comes before that, because we need a reference to the node that comes before the node we want to delete. That's this node 3 in this case, if we want to delete the node with 2. And then when it comes to actually deleting the node, we update this node's next to be its next. So we ask its next node, hey, just asking, but what's your next? And it's going to be like, oh yeah, I refer to this node over here. And it says, cool, thanks, that's my next now. And we just completely cut that node out of the list. So now when you're navigating this node, you go to this node, next. You never go to this node anymore. It's deleted from the list. And all we did was update one reference. We just asked the node for its next and then put that in this node's next and said, sorry, 2, you're done. You're out of this list. And if nothing else refers to this node, there might be some other code somewhere else on the stack that has a reference to this node, or in some object on the heap even. Could possibly be. What we effectively have is a linked list of size 1, a linked list of size 2, another linked list of size 2, and a linked list of size 3. We actually have 4 different linked lists, because a linked list is just a reference to a linked list node. So we do effectively have 4 lists. So something else could refer to this node, but if nothing else refers to this node, it's garbage collected, it's gone, it's out of there. We don't have a reference to this object, it's going to get garbage collected. And all we did was update this.next equals this.next.next. That's it. That's all we did. Completely cut it out of the list. So pretty easy to, conceptually anyway, to delete a node from a list. Code-wise, it gets a little tricky. Doing the navigating a list, storing 2 references simultaneously, and avoiding null pointer exceptions all throughout does get a little tricky. But that'll show me that you can write code, complete that learning objective. Write code that uses linked lists. All right, stacks and queues. Moving on. Stacks and queues in half an hour, which should be pretty simple to do. Stacks and queues, there's not too much here, and I don't really test you on stacks and queues. It's usually a bunch of interview questions is where I hit you with stacks and queues, and since we're not doing interviews, I mean, it is what it is. It's very important to know these concepts, though, of stack and a queue. The code, not as much, but the concept of stack and queue is just fundamental computer science information that you have to understand. In fact, we've been talking about a stack. We've been talking about the memory stack all semester, which is a stack of stack frames. So that concept will come up a lot. The concept of a queue and even code for a queue will come up when we talk about graphs. So important, but not immediately so. We'll be able to get it in half an hour with no problem. And these are restricted data structures. I always share my opinions on these. That I don't really like stacks and queues in code necessarily. I'll use them also, from time to time. But it depends on. It has to be a very specific application where I need them, like BFS when we talk about graphs. I'll use a queue for that. But these are data structures with restricted features, which never sits very well with me. So we have full functionality. Like when we build our stacks and queues, we're going to build them off of linked lists. So we have the full functionality of a linked list. But with stacks and queues, we're going to limit the features that we have to just a couple of methods in the name of efficiency. So we're going to use a linked list, but use it in a very restrictive way in order to make sure that the user of the data structure doesn't do anything dumb. Is effectively why they exist as classes anyway in code, which doesn't seem right. As concepts, very important. Use a linked list and just use it as a stack and use it responsibly. Very, very important concept in that sense. But the stack class that we'll see, there's no reason to ever use it. The queue class, there is some reason to use it. But all right, let's get into it. Enough preface. Stack is your classic last in, first out data structure. I always think of a stack of papers or a stack of folders in here. And when you have a stack, you can only add things to the top of the stack or remove things from the top of the stack. And that's it. Yes, technically you could pick up this pile and get the middle folder out of here. You could pick up the whole thing and add something to the bottom. But conceptually, in computer science, the concept of a stack, you can't do any of that. You can add to the top. You can remove from the top. That's it. And we call these methods push and pop. Push to add an element to the top of the stack. Pop to remove the top element from the stack. And when you pop from the top of the stack, that will also give you a reference to that top element. Or if it's like integers, depending on your implementation and everything, it might just give you the value if it's not a reference. Or I guess it always gives you the value, and the value might be a reference, rather. And that's it. That's a stack. Has these two methods, and that's it. Some implementations you'll come across will also have peak or top as part of its implementation, which will return the value of the top element without removing it from the stack, which can be useful in a lot of applications. But that's not a fundamental part of what the concept of a stack is. I don't know if I'm supposed to 51st and 137th out. 51st in 137th out. I don't know if I'm supposed to know what that means. I might be missing some context. But this is it. That's a stack. It has those two methods. And notice what's missing here. The important part, I guess not the important part, but the notable part is what's missing here. Namely, methods like size. You can't ask a stack for its size. You cannot take a stack and say, hey, stack, how many elements you got? Can't do it. Not with the concept of a stack. Now, somewhere out there might be a class called stack, which has push, pop, and size. That's fine, but it's not part of the concept. The fundamental computer science idea of a stack, can't ask it for its size. Yeah, I just missed the joke. So push and pop. Oh, and the reason, I'll mention this in a later slide, but I want to get it out of the way now. The reason for this restriction is that push and pop, we're going to implement both of them in O of 1 time. So we want them to be, every method to be efficient, very fast, constant time methods. And size is not constant time. Size is going to be O of n. Unless you have a separate variable to track the size, you could turn it into O of 1, where push just increments it and pop decrements it. We can do that, but it's not necessarily, strictly speaking, an O of 1 operation. So anything that's not O of 1, just don't let the user call it. So we're restricting the user and saying you have to only use these efficient methods, which is weird. Like, just as a developer, just don't use inefficient methods. But sometimes you want to use an inefficient. Sometimes you want to know how many elements are in your stack. So if you just use a linked list and call it a stack, then you always have that option to ask it for its size, for example. Later on, you can ask it, hey, do you contain this element? You can ask it those things and just understand that that's going to be an O of n method. It's going to take some time, that maybe you shouldn't, you should think about that decision. But to just say, no, I'm going to use this data structure that ties my hands behind my back instead is weird. But that is what we're going to do because, well, it's part of computer science. And for whatever reason, interviewers love to ask about stacks and queues and all these different data structures. So if I don't show you what they are, I'll be doing you a disservice. Do we need to be concerned with time, or will that come up in a later class? A later class. I'll mention runtime when it's like really relevant to what we're talking about. It's really relevant to the reason stacks and queues even exist. Is they only exist to give you these O of 1 operations. So I'll mention it in today's lecture, and a few other times we'll talk about sorting. Oh, actually we won't. We'll talk about sorting a little bit, but not really in terms of runtime. That got cut for the summer class. But it'll come up a few times, but you're not responsible for that content. You don't have to know the runtime stuff. CSE116, oh boy, that's all about runtime and proofs of correctness and stuff. So you'll be doing yourself a service if you pay attention to the runtime stuff I say, because this is a very, very light primer coat to a very heavy coat of paint that 250 is going to lay on you. So here's a stack. Here's how we're going to use our stack, and then I'll show you the code of how we implement the stack. But this is the idea of how we would use it. I'm going to create a new stack. It's going to have a type parameter. So I'm going to create a stack of integers. I'm going to push 1, 2, then 3. So 1, and then add push 2 to the top of the stack, push 3 to the top of the stack. And if I pop off the stack, X is going to get that value 3, and 3 is going to be removed from the stack. So pop removes the top element and returns the value of that top element. And here's how we do it. There's all the code. So for the stack class, this is going to look similar to your song class. It's going to look similar to that linked list of doubles class that we saw, in that it's going to be a class that has a linked list node as an instance variable, which is going to be the head of a linked list. Except it's a stack, so we call the head of the linked list the top of the linked list. So the top of the stack, as a reference to a linked list, is initially going to be null. We're going to initially have an empty stack. Again, this is not a new linked list node with the value of null. So don't do new linked list node null null. Don't do that. I don't know why I saw it. Last semester especially, I saw it so much. Just equal null. This is going to be our way of indicating that top is an empty linked list. When we push to the linked list, pushing is pretty simple to a linked list. We're going to prepend the same way we did in our very first main method where we had a linked list. We never wrote a prepend method, but if we did, it would be exactly this. We're going to create a new linked list node with the value that we want to prepend, or push in this case. And its next is going to be whatever the previous head of the linked list was. So top, if it's initially null, this is going to be null. So if we're pushing to an empty stack, this will just naturally work itself out where this dot top will happen to be null. So next will be null, and we'll have a linked list of size 1. We'll kind of get to initialize the linked list for free here without an extra null check. We never have to check if this dot top is null when we're pushing, because if it's null, well, that's what we wanted anyway. So problem solved. And then set the instance variable to whatever we just created, the linked list node that we just created, which is the new top of the stack. For popping, we do need a null check. If this dot top is null, so if the stack is empty, which this is, it depends on your implementation whether we do this or not. If the stack is empty, I'm going to return null. It's up to your implementation. A lot of implementations that are built into languages will just crash your program. If you try to pop from an empty stack, or we'll see in a minute, dequeuing from an empty queue, throws an exception and the program crashes and everything blows up. I'm going to return null, so we'll be a little bit safer in our code. Things don't completely blow up. We'll just return null. But in general, when you're using a stack or a queue, if it's empty, you should not be asking it to remove an element. Things should break at that point. I got lost in my head for a second, but we usually, in the built-in implementations, you usually have an isEmpty method that returns a Boolean, and that's how you would do your checks. Hey, are you empty? Because if you're empty, I don't want to ask you to pop. But that's not, again, it's not part of the fundamental concept of a stack, the computer science concept. It'll be a programming implementation of a stack. So if it's null, we're returning null. Otherwise, we're going to remove that element. We're going to get its value first because we don't want to lose that value. And then we're going to set the top of the linked list to the second element of the linked list. So this would be an example of removing the first element of a linked list. We're going to update the reference that contains our linked list to that reference's next value. So instead of referring to the first element in the list, we're going to slide that reference down to the second node in the linked list. And then we're going to return that value that we stored temporarily to make sure that we didn't lose it. We're going to return whatever that value was, because that's what the user wants. So we updated the top of the list to be the second element in the list. So we removed it and returned the value that the user wants. And then I guess toString is just calling the linked list toString. I'm not sure why I had that in the slides. Oh, damn it. This is everything I just said. Okay, so visually, we have this stack. We pushed 3, and that got next of null because the top was originally null. We pushed 7, so top would refer to 7, which refers to 3, which refers to null, and then push 2, update top to this new node. And then when we push a new node, like -5, we're going to create the new node. Its next will be a reference to the old top of the list, and then update top to refer to the new node that was created. And notice that when we push this node, which in this red box, nothing in here changed. We didn't have to change the original stack at all to add an element to it. And more generally, if you want to prepend to a linked list, you actually don't have to change anything with the linked list. We get a reference to a new linked list node, but that linked list node reuses the entire original linked list that it was prepended to. So a neat factoid that was critically important when we taught the course in Scala. Now it's just kind of like, hey, look at this. It's kind of neat. In Scala, that made a huge difference. That fact did. And then so now I don't have to talk about it so much. Now stack.pop, we're going to take that top and have it referred to the second element. So we're effectively cutting this -5 out of the list, and then we would return -5, and that would be stored in our X in this instance. So we're updating the reference top refers to the second. So top equals top dot top. In this one, top equals top dot next, which is a reference to this node. So top equals that new reference. Or not new reference, but the reference that it was referring to as its next reference. And if nobody else refers to this stack, this node is beginning garbage collected. It's gone. Thanks to Java for cleaning up things for us. I already mentioned this slide, so I don't think I want to talk about this stuff again. We're restricting ourselves to O of 1 operations. Push and pop are both O of 1. There's constant amount of work in either of those. We're not navigating the linked list at all. It doesn't matter if this is a linked list of size 1, a stack of size 1, or a stack of size 1,000,000. These methods do the same amount of work either way. There's no recursion that's navigating the stack. There's no loop that's navigating the stack. Doesn't matter how big the stack is. Pushing and popping, same amount of work no matter what. That makes it O of 1 or constant time. And we don't have any of our O of n algorithms. Two strings, we actually do have two strings sitting here, which is just really weird. That shouldn't be there. It's there for the examples in the repo when there's a main method and you can actually print it out to see what's in the stack. It's not part of the stack conceptually, so it's weird to have in my slides. But size, find, append, none of these are going to exist in a stack. Queue is our first in, first out. It's a standard. You queue up, you wait in line. When you get to the front of the line, you're up. So you can only queue in queue to the back. You can only dequeue from the front. And those are exactly what our methods are. Instead of push and pop, in queue and dequeue, the only difference is that we're going to be working on both ends of the linked list with a queue, which complicates things a little bit. So let's talk about it. So with a queue, if I have a queue and I want to add 1, 2, then 3, so the front of the queue, 1 is the very first person into the queue. They're first in line. Get 2 in there. They have to queue up behind 1. 3 is going to queue up behind 2. So 3 is at the back of the queue, 1 is at the front. And then when we dequeue, we're going to pull from the front. So 1 would be dequeued, X is going to have the value 1, and that node with the value 1 is removed from the queue, and 2 is now at the front of the queue. So conceptually, that's what we want to do, code-wise. It's about the same complexity as a stack, but there's a lot more code just because there's more null checks and more references to keep track of. So it's not too much more confusing. Let's go through it and you can see what I mean. But there's just more checks that we have to do. Things are a little bit different in the way that we have to handle things because we have to work on both ends of the linked list. So if we just had a reference to the front of the linked list, whenever we want to work with the back of the linked list, we would have to navigate the entire queue, which is going to be an O of n operation, which we just don't allow. In queue and dequeue have to be O of 1 operations. It has to be a constant amount of work. And the way to do that is to store references to the front and back of the queue. So we have 2 references to track. They're both going to initially be null when the queue is empty. And then when we in queue, we're going to check, is the back of the list null? If the back is null, the front is also null. So we could also say this dot, if this dot front equals null, it'd be the same check because either they're both null or neither of them are null. So we're going to check if one of them's null. That's an empty queue. If it is, we're going to, if it is empty, then when we in queue this value, we're going to create a new linked list node with that value and next of null, which is the entire queue. And then front and back will both refer to that same queue. In fact, I could flip around both front and back here. This could say front, 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 back, and this would do the same exact thing. We're getting front and back both referring to a new node with the value that we enqueued. But if the queue is not empty, then we're going to go to the back of the queue, set its next to a new linked list node with the value that we're enqueuing. So we're enqueuing this node at the back by effectively appending, but appending took 2 steps. We find the end of the list and then we append. But here we already know the end of the list. We already have a reference to the end of the list. So we're just going to do the append, which is constant time. And we're going to update the reference of back to be that new node that we just created. Then when we dequeue, again, just a few more checks that we have to do. If the front is null, we have our case where what do? Do we crash the program? Like, what do we do? We're just going to return null. So we're going to be a little safe. We're not going to just crash everything. If the queue is not empty, we're going to get the value. This is going to look similar to the stack. We're going to get the value at the front because that's what we need to eventually return. We're going to get the values, the next value, and set that equal to the front. So we're going to update the front to be the second node in the queue instead of the first node. So we're dequeuing that first node. And then the extra check we have to do, so everything I explained is the same as the stack. But the extra check we have to do is if we dequeued the last element of the queue, front is going to be null. But at that point, back is still going to be referring to that node that was the front, because at that point of one element, front and back are referring to the same node. So if front is null, that means we better set back to null, because we don't want back to be referring to a node that has been dequeued. So an extra check, if we dequeued the last element, front and back are out of sync, so let's sync them up to both be null, because we have an empty queue now. And then toString, which I got to remove from my slides. Oh, damn it. I did it again. All right. Well, I already said all this stuff. So if you want to go back and read it, you know, it's there. I always lecture from the slides that are on the repo. I download the slides, even though I already have them on my hard drive. I download them right before lecture, just as a show of faith that I'm lecturing off of the same exact slides that you have access to. So you have access to the slides if you want to go back and read those. But it says the same things I just said. The bullet points are mostly there just for if you're studying off of the slides. They're not necessarily there for me to lecture off of. They remind me of things every once in a while, but I kind of don't look at the bullet points, which is why I get out of sync with my slides. Anyway, let's wrap this up. So let's do the same thing in our abbreviated memory diagram format, how a queue works. So we're going to create a new queue, and this one I'll go through all the steps. Queue has a few more moving pieces with this front and back reference. So let's go through this in more detail. And this one will be like a legit abbreviated memory diagram, but still not like the full details. At this point, I do start assuming that you understand the structure of a memory diagram, that I can leave out a lot of the details, especially for this. This lecture would have like 10 memory diagrams. I would never be able to fit them all in. And I believe I can get away with that. When we in Q3, we're going to create, initially front and back are both referring to null. We in Q3, we're going to create a single node with the value 3 and a next of null. And front and back are both going to refer to the same node at that point. When we in Q7, front and back are going to get out of sync for the first time. Front is going to still be referring to that first node that was enqueued, but back is going to have a reference to that second node, that node that was just enqueued. Whatever was just latest enqueued, that's what back will refer to. And the first node is going to refer to the second one. We're building a linked list still. We just appended 7, but we had to update this reference back to make sure it refers to the new node. And same when we in Q2, we append that to our linked list and make sure we update our reference back to make sure it is referring to the last node in the linked list. And we're going to dequeue from this list. We're going to dequeue 3, so X is going to be 3 at this point in time on the stack. On the memory stack, I guess that gets confusing in the lecture with stack and queue. But in the memory stack, the variable X will have the value 3, and we update front to be a reference to the next node, and then that original first node that was enqueued, that was just dequeued, gets garbage collected, it's gone. It's a candidate for garbage collection. We're going to dequeue again. Now front is going to be referring to 2. So 2 is the only element in this queue at this point in time. This node gets garbage collected, and X is going to have that value 7, which it just got from this node. Going to dequeue again. At this point, front and back will both be referring to null. And this is where, on the previous slide what I was talking about, we can get front and back out of sync. So if we dequeue, front is just naturally going to get the next value, which is null. So front will just be referring to null, and that's all fine. And we have to check, if front equals null, that's going to mean that back is still referring to this node, which just got dequeued, which is not what we want. Back can't be referring to a node that's not even in the queue. That's just asking for some really crazy bugs. So that's our check. If front equals null after dequeuing, back better also be set to null to make sure that we indicate the empty DQ again by front and back both referring to null. We can't have one referring to null without the other referring to null. And then if we DQ again, what happens? We already had this conversation, so I won't go through the whole thing again. But what happens? Our code is going to return null the way we saw it. So X would get null, but what actually happens, because X, null is the lack of a reference. What actually happens is the program crashes. But null is the lack of a reference. So if you have a variable that's supposed to store a reference to an object on the heap, then null says, okay, I don't actually refer to anything. I'm supposed to, but I don't refer to anything. I'm not doing my job. I just got null. I got nothing to tell you. But X is of type int. Int is a primitive. Int's job is not, X's job here, since it's an int, is not to refer to an object on the heap. Its job is to store a value. A value that's an integer value, a 32-bit value that represents a positive or negative whole number value. It gets null, and it says, what the hell am I supposed to do with this? And the program crashes. You can't store null in a primitive type. It doesn't make sense. It doesn't work. And Java just says, I ain't having this. I'm crashing. Deal with it. So the program actually does crash here. But what should happen, that's up to your implementation. Like I said, most built-in queues in programming languages will throw an exception and crash if you try to dequeue from an empty queue or pop from an empty stack. Ours returns null, but we're still going to get an error because null can't be stored in a variable of type int. Oh, it was the last slide. Hey, with 2 minutes to spare. Cool. All right, any quick questions in 1 minute? 2 minutes, minute and a half? Do I have any announcements I should talk about? I think I covered it all at the beginning of the lecture. Just a reminder, quizzes on Tuesday. I'll send out an email to everyone in the class at 11 a.m. Eastern Standard Time on Tuesday, June 13th. I'll email you the code for the quizzes. And then you'll have the next hour to do your quizzes, so till noon. And then, especially being the first one, I'll give some leeway. I'm thinking 15 minutes to make sure that you have ample time to get your quizzes in electronic format, take your pictures, scans, whatever you're going to do, and get them submitted. And then at 11:15, if I settle on the 15 minutes, I think 15 minutes is the right number. At 11:15, at 12:15, that's when I'll start the stream and start lecturing about testing, which is our next lecture is our very first live coding lecture. So next lecture is just live coding. I have no slides, and I intend to spend a lot of time in the debugger showing you what the debugger even is. I might skip some of this testing with structure and testing linked lists and trees. I might skip some of that and get to the debugger since we lose so much time for the quizzes. Because the debugger is super useful for writing your code, and testing with structure and testing linked lists, not as much. I thought testing with structure, what I have prepared for that, I thought was going to be more helpful. But the way I have the tasks set up, the way I show you in this lecture, just ended up not being super useful. Where do we submit the quizzes? Autolab. So both quizzes, we are making memory diagrams, or the second quiz is handwriting code. Both quizzes are memory diagrams. I'm going to give you 2 programs, one for classes 1. So the classes 1 quiz will have the classes 1 program, and another program for data structures 1. You're going to make 2 memory diagrams, and you're going to submit them to Autolab. Yeah, reviewing everything we've learned so far is a good idea. It's any of the memory diagram stuff. And it is, like, the memory diagrams are, like, classes 1, it corresponds to this lecture. Data structures 1, that corresponds to today's lecture. But just incidentally, lecture 1 and lecture 2, it's just fundamental concepts that those happen to just be in the quizzes too. Because, I mean, you need a loop in Java. You need to be able to read a loop in Java. There's just things like that I can't really avoid. There won't really be unit testing on the quizzes, though. Unit testing, I'm hitting you with unit testing on the programming tasks. So they don't really show up on quizzes. A lot of info to take in today. Every lecture is going to be Every lecture has been, and every lecture will be a lot to take in. Actually, I take that back. There's a few exceptions. Lecture 5, this is designed to be a nice cool down after the quiz. I'm going to show you the debugger. It's mostly just tips and tricks, I would say, on how to debug your code, so you're not completely lost when you have a bug in your code. Giving you tips on how to approach these programming assignments when something goes wrong. That's what most of Lecture 5 is about. And also Testing 3. This is going to be the same way. Oh, yeah, I gotta cover files and exceptions. I do actually have to cover some content that you're going to be held accountable for. Yeah, Program Task 6. I gotta show you how to do Program Task 6. But Lecture 5 will be the one exception. Notice there's no programming task associated with this one. There's no quiz associated with Testing 2 either. This is just meant to be a cool down from the quiz and help you with the homework. That's the only one I could really fit in there, though. Which I'm surprised I could do that. I'm surprised I got one. Oh, and I guess, now that you mentioned it, and Lecture 10, or Lecture 11. Just because it's Lecture 11 and Lecture 12. Lecture 12 is just going to be quizzes, a bunch of quizzes. There's no lecture at all. But Lecture 11, I have no chance to assess you, especially when it's pass-fail. Like, you have to pass everything. I can't cover new material on Lecture 11, because when would I assess you that would make it fair? Like, you don't even have a full week to learn it, apply it. Like, it just wouldn't make sense to hold you accountable for anything that's covered on Lecture 11. Not with this grading scheme. If it were percentage-based, fine. With my grading structure, no. Can't do it. Not going to do it. Cool. All right, I'm signing off. I'll still have office hours today. Since we just hit a deadline, I don't know how busy it'll be, but I'll be there. Anybody who has questions. Me and Gerline both have office hours on Thursdays. So we'll both be in there. So if I don't see you in office hours, I'll see you on Tuesday, and good luck on the quiz. Take care, everyone.